Hi, welcome to this fourth session on machine learning. So last time we talked about stationary time series. Today we're going to talk about important concepts that tell us whether the time series is stationary or not. So the first thing is called null hypothesis. Connected to this is something called unit root, and then a very important tool in a machine learning programmer, data scientist, whatever you want to call them, arsenal is the ADFuller test or augmented Dickey-Fuller test. So let's come back to the original concept that we need a time series that is stationary to be able to use AR or MA kind of concepts. And just to refresh, if a time series shows some kind of a trend as time progresses, it's not stationary. What is stationary is if the means is more or less constant when you select time windows. This is more or less stationary. So we need stationary time series to be able to create models that will predict. So far, we have been doing visual inspection. So we plotted ACF and PACF graphs or normal plots and saw visually whether the time series is stationary or not. So the blue one is stationary because the mean remains more or less the same across the time that we are traveling, whereas the black is not because the mean keeps changing. So the question is, how do I know that something or input values are stationary without visually looking at it? Because remember, this is a mistake most people do. When you deploy your piece of code in production or on a machine and you make it run, there is no human being looking at the plots to decide whether the incoming data is stationary or not. So you have to be able to mathematically and / programmatically be able to compute that. So the first concept is null hypothesis. What it says, or rather before that, so what we're trying to do is we're trying to predict a variable y based on past values and so on and so forth. I can very well say that if I am able to predict the current value of y based on past values of y, it means there is a relationship between these values. Null hypothesis states that no relationship exists between two values, or in very simple terms, if I am trying to predict y, which is based on some function of x, so between x and y there exists a relationship. If null hypothesis is true, then there is no relationship that exists between x and y, and therefore I cannot form this equation. I cannot say y is equal to some function of x. Remember, we are trying to, in machine learning, trying to predict the value y based on some input value. Therefore, if null hypothesis is true, I will never be able to find an equation between the independent and the dependent variable. Thus, for us to be able to create a model, the null hypothesis must be false. Again, null hypothesis basically takes the default position that there is no relationship between two measured values. Now, How do we know, or how do we figure out that this is false or true? There is something called unit root, which is where we come to the second point. Now this is where the math gets a little complicated, so I will try and oversimplify, even though I might be a little wrong on math, but I have to simplify because this is for beginners. So let's go back to the equation that we were trying to model, the regression equation, that y at time t is equal to alpha 1 yt minus 1 plus alpha 2 yt minus 2, and so on and so forth. Now there is a concept in math which is called the characteristic equation, and without going into proof and other theorems, if I have to solve the characteristic equation, or before that, the characteristic equation can be written as mp minus mp minus 1 into alpha 1 minus mp minus 2 alpha 2, so on and so forth, to an extent of alpha p is equal to 0. This is some kind of an equation where if the value of m is equal to 1, at which this equation becomes 0, we say this characteristic equation has a unit root. So this equation has a characteristic equation. Now if, mark my words, if this characteristic equation has a root, means solution, which is value 1, then such a process is not stationary. Now this is interesting because if it is not stationary, then null hypothesis is not false. Now connect these two. If null hypothesis is true, then the equation is not stationary. Or if null hypothesis is true, which means no relationship exists between the two variables. Number 2, if the characteristic equation has a unit root, then the process is non-stationary. So therefore, two results we have derived. One is presence of a unit root tells me that the process is not stationary, therefore I cannot model it. I must make the process stationary, or I must make the values stationary. Second, if null hypothesis is true, then there is no dependence between those two variables. Hence, unit root must not exist. So unit root must not exist, and null hypothesis must be false. When these two conditions are met, then we are good to say that we have a set of data points that are stationary, and we can create a model to make a prediction. Therefore, the question is, having understood these concepts, what can help us determine that unit root does not exist and null hypothesis is false? This is where the augmented Dickey-Fuller test comes in. What does it actually do? So now assume I have a set of values. So y is 0, 5, 9, 20. I'm just taking some random values. I need to know if these are stationary or not. I have two options. One, I can actually plot a graph and say, visually look at it, and then I can say whether it is stationary or not. But this is exactly what we're trying to avoid. Because, as I said before, when we deploy this code, there is no one looking at it. It is running behind the scenes. So, given this set of values 0, 5, 9, 20, so on and so forth, so 0, 5, 9, 20, something like that. If this is not stationary, remember we have to make the value stationary. So I have to do two things. One, check if stationary. Two, if not stationary, then diff. Remember diff, and then check again. Go back to step 3 is go back to this again. So what am I doing? I have these data points. Again, let's take the same data points. Y, 0, 5, 9, 20. If I actually plot them, then it seems to me that first one is here, 5, maybe 9 here, and then 20 here. So this definitely is not stationary. However, if I take y dash, where first value 0, here I'm using Python, I have nan. So nan minus 0, so I get nan. Now I subtract from 0, 5, so I get minus 5. I subtract from 5, 9, I get minus 4. I subtract 9 from 20, I get minus 11, and so on and so forth. Now if I plot this graph, I ignore this nan, I get minus 5 somewhere here. At 0, now this is shifted. Then I get minus 4 somewhere here. Then I get minus 11 somewhere here. And this process continues. The graph has changed. Now, so what I do is I will keep doing diffs. Doing a diff means taking the values A0, A1, A2, and so on and so forth. If this is my y values, y with diff equal to 1 would be, first value would be nan, second would be A0 minus A1, third would be A1 minus A2, and so on and so forth. And then I drop this and I come up with A0 minus A1, A1 minus A2, and so on and so forth. And if I name them as, let's say, B1 or B0, B1, and so on and so forth. So y with diff 2 would be equal to nan, and see this, B0 minus B1, B1 minus B2, and so on and so forth, and then drop this again. So this we will keep doing, and every time we get this value, we will run the ADFuller test. So we will say result is equal to, let's say there is a function named ADFuller that performs this test and tells us whether we can reject null hypothesis or not. And I pass on the values of y which are diffed by n. So the result that we receive is an array, and in this result the ADFuller test will give us a number, and we will see now how it is implemented in Python. That number should be less than 5% or 0.05. It effectively tells me that when I get in the result the ADFuller, after calling the ADFuller function, if my result is less than 5% or 0.05, then this time series perhaps with 95% confidence we can say is stationary, and we can reject null hypothesis, which means the formula using which we create this time series. Remember, yt is equal to alpha 1 yt minus 1 plus alpha 2 yt minus 2, and so on and so forth. So the formula rejection of null hypothesis means that the time value of y at time t is indeed having dependence on previous values, and no unit root exists. So that is the importance of ADFuller. Now you have come to a point where you don't have to visually look at the plots to decide. You can write in your code. So let's see how we can write a pseudocode. So I will have a value for doing difference. First time I will have diff as 0, and I have my y values which is coming from somewhere. This is my original samples. Now here is what I will do. I'll say result is equal to compute the ADFuller function on y. Now if so, I will actually now I will do a now while result is greater than 0.05, right? So I computed ADFuller and I got a result which is greater than 0.05, which means I have less than 95% confidence that this current one is stationary. Now therefore I will again try and do another diff. So d is plus equal to 1. I increment d. Now I create y is equal to y dot diff, and this time it is d. Now remember, d would be 1, earlier it was 0, so now we have done one diff. However, every time we do a diff, the first value will be nan. So y would be, let's say there is a method called remove nan on y. So I have got my new value, and then once again I compute the result as ADFuller on this y, and this cycle will continue. After a few cycles, if my data is in such a situation where it can be made stationary, because not all data points can be made stationary no matter how many times you try, so you should probably have some kind of a limit here. Let's say if b is greater than 10, then break. We can't make this data stationary. It's perfectly possible. However, let's, for the sake of this discussion, let's assume after a few tries we will be able to do a diff, and we will be able to get to a point where the data will become stationary. So when we break this loop, the value of d will tell us how many diffs does it take to make the data stationary. And in ARIMA, A-R-I-M-A, this d gives me this value of I. So when I use, which is our next session as to how to use ARIMA algorithm to create a prediction, we first have to ensure that our time series is stationary, and to make that stationary, how many diffs I have to do, and this ADFuller concept will tell me how many diffs I have to do without actually doing manual intervention, or sorry, without actually requiring a human being to look at it. So now let's look at how we can write code to achieve the same. Okay, so let's understand how we can use ADFuller in Python and check if a series is stationary. We can reject the null hypothesis, and does it have a unit root or not. So the one pandas and numpy and matplotlib you identify easily. There is a new thing that I have added here. This is from stats model. I am importing ADFuller. Additionally, I selected a data set I downloaded from the internet. This is about energy production. You can use any other data set. So let's try, and so my data set is in a CSV, and let's just print what this data set is. Okay, so I have the date, and by month and year and date I have energy production. Let me just rename this column. Now let's see, everything should be okay. Yeah, so I have my energy production column. Now I can do the usual way and plot this. 23, and then let's see, plt dot plot. I am plotting these many values. So np dot range, I can say df dot shape 0, that is the number of rows, comma df production show. So let's see. Yep, so I have about 450 odd values, and this is definitely not stationary because we can see a trend. So remember what I said, we will be writing a piece of code which was this one, and we will use ADFuller to figure out automatically how many diffs does it take to make this stationary. So let's go back to our Jupyter code. So we have y, which is equal to, I'm just simplifying this so that, yep, I have all the energy production values. So this is my y. Let's define a variable diff that will tell me how many diffs I am doing. So now I will compute result ADFuller of y, and let's print result. This is an object where the most important thing for us to see is this second value. This is 0.0865, which means about 8.65%. Remember what I said. This value must be less than 0.05 or less than 5% for us to say with 95 or more percent confidence that we can reject A, null hypothesis, B, unit root does not exist, or alternatively the values are stationary. Now, so we will do y result, the second value is greater than or equal to 0.05. We will first diff is equal to diff plus 1. We need to do a diff. Next, we will say y is equal to df energy production dot diff, and it is diff dot values. So this y is now replaced. Now remember, whenever I do diff, the first one is nan, so I will replace y with not np dot is nan y, and then I will again compute result is equal to ADFuller of y. What is happening? I compute ADFuller of the original values. If I get the second value, which is my p value, greater than 0.05, then I increase this diff value. I diff the values that many number of times, and then I remove all the odd numbers, and then I again compute ADFuller. If this time the result is less than 0.05, it will break and it will come out. So let's print here. Print diff is equal to diff. So it is 1. Now let's see and plot the same things and figure out if it is really stationary. So np.arange length of y, and I will plot y here. I'm plotting y because now this y is after diffing the values. So let's see. Perfect. Visually we can see that the values are centered around 0. This is stationary. Therefore, this very simple concept of using Dickey-Fuller test or augmented Dickey-Fuller test in this little while loop will help us figure out the value of D, the number of times we have to diff the values to make it stationary. And the moment it is stationary, we are now good to go to create our model using which we can do prediction. And in the next session, we will learn ARIMA, auto-regressive integrated moving average method, where I, the integrated, is the one where we use this value of diff. Until then, if you find any issues, errors, or you need clarifications, please use the comment box below and let me know. Thank you. Bye-bye. See you in next session.